Hello friends, welcome to my YouTube channel RF Design Basics. So in today's lecture, we are going to discuss about the Poisson's and Laplace's equation. From the Gauss's law, we already know that the del dot D, that means the divergence of electric flux density, is equal to volume charge density. This is also called point form of the Maxwell equation, which is the equation 1 of the Maxwell equation, which is in the point form. Also, we know that the electric flux density and the electric field intensity is related with D equal to epsilon E. And from the potential formula, the electric field is given by minus of gradient of potential. Using these three informations, we are going to derive a new equation which will be called as Poisson's equation. So for that, let us take this Maxwell equation and replace this D with epsilon E here. So it will become del dot epsilon E equal to rho V. Then further, this E can be replaced with minus del V. So in place of E, let us write minus del V, and it is still a vector quantity. So if we take divergence of a vector quantity, here epsilon will be scalar, so we can take it out. Minus sign also will come out. So we have minus epsilon, and divergence of gradient of V, we will show this as del square V, which is equal to rho V, and hence del square V equal to minus rho V by epsilon. So this equation is called Poisson's equation, which is given by Poisson. If we assume that the volume charge density is 0, if we say volume charge density rho V is 0, that means we are talking about a case where volume charge density is not present, but line charge density or point charge or surface charge density may be present. So rho V equal to 0 if volume charge density is not present. In that case, this equation will convert to, if we put rho V equal to 0, this will become del square V equal to 0. So in that case, this equation is known as Laplace equation. So here, first of all, we are going to discuss about this new term, which is del square and often known as double delta. And this double delta we are going to find out, as we know that from the divergence formula, that del dot A, that means divergence of a vector A, is given by del AX by del X plus del AY by del Y plus del AZ upon del Z, where AX, AY and AZ are X, Y, Z component in rectangular coordinate system, and the gradient of V, any scalar, gradient of any scalar is given as del V by del X AX plus del V by del Y AY plus del V by del Z AZ. So here we can see that del V by del X is the component in X direction, del V by del Y is component in Y direction, and del V by del Z is component in Z direction. So when we take divergence of this particular vector, as it is vector, so the divergence of the gradient of V will be equal to, we are going to apply the divergence formula from here, and we have AX as this value. So in place of AX, we are going to put this. In place of AY, we will put del V by del Y, and so on. So del by del X of del V by del X. So we are doing partial derivative 2 times So it is del 2V by del x square plus del 2V by del y square plus del 2V by del z square. And this is nothing but the double delta del 2V. So we can say that in rectangular coordinate system we have formula for the del 2V as this, and based on the divergence and gradient of other coordinate system we can write del 2V for other coordinate system as well. So del 2V in cylindrical coordinate system will be equal to 1 by rho square del by del rho of rho del V by del rho plus 1 by rho square del 2V by del phi square plus del 2V by del z square. So this is in cylindrical coordinate system, and similarly we can find for a spherical coordinate system. To know how to write divergence and gradient and curl in cylindrical and spherical coordinate system, you can refer my video where I have discussed about how to memorize this gradient, divergence and curl in different coordinate system, and you can apply that to find out the Laplacian. Here we call del square as Laplacian operator. So Laplacian of V in a spherical coordinate system as 1 by r square del by del r of r square del V by del r plus 1 by r squared sine theta del by del theta of sine theta del V by del theta plus 1 by r squared sine squared theta del 2V by del phi square. So this is Laplacian in a spherical coordinate system. So using this formula we can find the Laplacian of given potential. So now we are going to discuss about uniqueness theorem, which says that for any given equation del 2V equal to 0, there will be one and only one solution. That means the solution is unique. So the theorem is known as uniqueness theorem, and we can prove this by taking two different solutions. Let us say V1 and V2 are two solutions which satisfy this del square V equal to 0. As we know that if these are the two solutions, it is going to satisfy this separately. So del 2 V1 equal to 0 and del 2 V2 equal to 0. If we are able to prove that V1 and V2 both are same, we can say that there is only one solution possible, and that will be the unique solution, and hence we can prove the uniqueness theorem. So to start with that, let us take these two equations and first take the difference of these two. What we will get is del 2 V1 minus V2 equal to 0. Remember, here we have second derivative of V1 and V2, so we cannot say directly that V1 equal to V2. If we have V1 minus V2 equal to 0 only, then only we can say V1 is equal to V2. If there is any operator here, we can't directly conclude that V1 is equal to V2. So for that we are going to do some operation here. And first of all, let us say that at boundary, because the problem is only one, so solution may be two, the problem is only one, so the boundary condition will be only one. So for both the solution, the boundary condition must be satisfied. So if I say V1b is the potential at boundary, it must be equal to V2B for the second solution, and let's say the overall value is BB, which is common for both. So the difference V1B minus V2B must be equal to 0. So this we are going to use in future. As of now, let us take this equation again and write one trigonometrical identity to find out the relation, and for that the trigonometrical identity is divergence of VD equal to V divergence of D plus D dot del V. So this is going to be true for any value of vector D and a scalar V. Here D is vector and V is a scalar. Now what we will do is, we will assume that vector quantity which is D here, because this is going to be valid for any vector quantity, so this D vector I am just assuming as del V1 minus V2, because this is gradient of potential, so it is going to be vector, and V is V1 minus V2, so this is difference of potential, so it is going to be scalar. So this I am going to apply in the equation. So let's apply that and see what is happening. So del dot D, del dot VD, V1 minus V2. For D we write del V1 minus V2 equal to V. So V is V1 minus V2. Then we have del dot D. So del dot del V1 minus V2 plus del V1 minus V2 dot del, and then V is V1 minus V2, and write the left side equation as del dot V1 minus V2 and del V1 minus V2 as equal to V1 minus V2, and this will become del square. So V1 minus V2 into del square V1 minus V2 plus, since both are same, this is one vector, this is another vector which is having dot product, so it will be square of this dot product, and we can write del V1 minus V2 square. Now integrate this using volume integration on both sides. So we have to put a dv here, volume integration, dv here, here also volume integration and dv. Now take the first term here in the left hand side and see v1 minus v2 is scalar, so it is in the multiplication of the integrand, and here it is a divergence of some function dv. We know that volume integration divergence of any vector, here the vector is this, divergence of any vector is equal to surface integration, that means closed surface integration of d dot ds. So in this case we have v1 minus v2 as a scalar, we can take it out, so we can take v1 minus v2 out, and inside we have del v1 minus v2, then we have dv. So del v1 minus v2 is the function dot ds. So volume integration is converted into surface integration, and this will be for the closed surface. Now if it is a closed surface, there will be value on the surface boundary, and that boundary condition is v1b equal to v2b equal to vb. So if we put in place of v1, v1b, in place of v2, v2b, and take the difference, and the difference was 0 because both values are same. So we can apply that here and we can say that surface integration of this function is going to be 0. So LHS is 0. Now in RHS we have two terms, first term and second term. So when we take first term, we can see that it is having del square V1 minus V2. So this term, which is a kind of constant term, because dV is volume integration, this V is potential, this V is volume integration. So del square V1 minus V2 was 0 from our assumption, because here we have taken del square V1 minus V2 equal to 0. So this is 0 from the assumption. So in the right hand side, the first term is also going to be 0. That means it is 0 equal to 0 plus this quantity. So this quantity must be 0. And if we solve that, we can find our result. So we have volume integration of this quantity, which is del V1 minus V2 square dV equal to 0. Now see, any integration may be 0 if the integrand, here integrand is this quantity. If integrand itself is 0, there are two reasons. First reason is if integrand is 0. If integrand itself is 0, the integration of that will be 0. And second possibility is integrand is positive and negative in some region. So in some region it is positive, in some region it is negative. So overall effect of integration is going to be 0. For example, if you take sine x function and integrate it from 0 to pi, so from 0 to pi, sine function is positive. From pi to 2 pi, it is negative. So overall integration from 0 to 2 pi is 0 only if it is having some region positive, some region negative. Here, this function is a square of something which cannot be negative for some reason. So it means that the second reason is not valid. So first reason is valid, means integrand itself is 0, and we can say that this function itself is 0. So you can write del V1 minus V2 square must be 0. So this is saying that del V1 minus V2 equal to 0, and if the gradient of any function is 0, it means that this function is constant. Now we have to find this constant term by applying the boundary condition, and that boundary condition is V1b minus V2b equal to 0. So if I apply the boundary condition, we will get constant term as 0, hence V1 minus V2 equal to 0, which says that V1 and V2 are identical. So V1 and V2 are identical. So the solution of del square V equal to 0 will be always unique. So this was the uniqueness theorem. In our next video, we will discuss the application of Laplace equation for the capacitance calculation. Thank you.